Yeah. Thank you very much. Thank you everyone for being here. It's a big honor being first talk of the semester. Hopefully I'm up to the task. And I want to talk about a paper that came out this summer that I wrote with Adar Sharon, who's another one of the new postdocs. He's going to be here any day now. He arrived yesterday, I think. He should join us in a day or two, I guess. And Eugene Jane, who was a postdoc at the Simon Center as well, and now he's in Beijing. And the point of the talk is to try and say a few things about symmetries that are both non-invertible and continuous. Everyone knows what a continuous symmetry is, but maybe not everyone knows what a non-invertible symmetry is. So I'm going to spend 5-10 minutes giving you a quick overview of the things that matter and why you should care about these things at all. Okay, please stop me at any time. If you have any questions or anything is unclear, I'll try to keep everything as pedagogical as possible. Okay, so let me begin with a review/motivation. And so I'm going to consider a very concrete example, which is the simplest QFT there is, which is two-dimensional Ising. Okay. By two-dimensional, I mean 1+1. Okay, so this has a very important fact about this theory is that it has a Z2 symmetry, which is just this. Okay. This is the symmetry that gives you like spin up, spin down if you want to realize this as a lattice model. Okay. And a very trivial consequence of this symmetry is that the correlation function x1, x2, x3, this vanishes because it's odd under this symmetry. Okay, it's odd, so it means it must vanish. But actually, if you solve this theory and it's actually exactly solvable, so you can solve it explicitly, and if you compute this correlation function, it also vanishes if you compute the 60. So you, instead of inserting the spin, you insert the energy, this correlation function vanishes, even though it's even under the symmetry. So it seems that there is some selection rule that doesn't come from any symmetry. And this is usually very weird. Every time you have some selection rule, there has to be some symmetry that explains it. Okay. So this is a very mysterious fact, the fact that this vanishes. But it turns out that there exists some operator D that commutes with the Hamiltonian, in fact, with the energy momentum tensor. And under this operator D, phi squared is minus phi squared. And now you see that
statement, like you have to tune to the critical point for this.
Yeah, this is sorry, this is a critical. Yeah. This is the criticalizing model, so steps. Sorry.
But there's their way to see in this field theories.
In the field theory, how to see this? Well, this is the ground, so I need to like it's like one of the Berliner lines of the Ising model.
I agree how to see it. I know how to see it in the CFT to see by the fourth.
But the fight or fourth is presumably not there.
That's what I thought. Yeah. So this is sort of emergent.
Well, yeah, exactly. Yeah.
Okay, fine. Yeah.
Okay, so this symmetry here explains why the correlation function vanishes. But this has a very weird property, which is that here I'm telling you how it acts on phi squared, but if you compute how it acts on phi, this is 0. First of all, these two equations seem to be incompatible with each other. But second of all, this equation tells you that D is not even a unitary thing because it's something that kills some operator, so you cannot have an inverse. Okay, so this seems to go against what we think about symmetries, in particular the Wigner theorem that tells you that everything is unitary. So a natural question is this thing a symmetry or not? Okay, so first of all, it does commute with Hamiltonian, so it seems that we should call it a symmetry. Second, it gives you some selection rule, which is correct. If you compute the selection rule that it predicts that this thing vanishes, and if you compute it, actually vanishes. So it's giving you something that is a correct selection rule. But at the same time, it's not a unitary operator acting in your Hilbert space, and in fact, it doesn't even satisfy a group law. So if you compute, for example, the square, this is 1 plus C, where C was the thing from before. So this is not even a group, it's an algebra, right? So we call this type of thing a non-invertible symmetry. And it has many of the same properties as a regular symmetry, but not all of them. So it differs from regular symmetries in some aspects, but it shares some other aspects with them. Okay. And it is actually a thing that people have been very interested in recent years, because apparently many of the theories that you care about have these type of symmetries, and in fact, they sometimes explain things that were very mysterious before people realized that these things existed. So, for example, to give you some concrete examples in 4 dimensions, turns out that a similar symmetry of this type explains a mild puzzle that appears in pi and dynamics. I'm not going to go into the details, but if you're interested, you can ask me later what the puzzle is, how this symmetry explains it. So pi and dynamics. It also appears in some natural extensions of the standard model, and it explains things that, for example, why the neutrino is so light. It also explains why the theta parameter of QCD is so small, etc. So many of the problems of naturality with the standard model, if you go to some extensions of the standard model that are kind of natural from the point of view, from the phenomenological point of view, these extensions have non-invertible symmetries, and those symmetries explain why these things are so small. Okay. Also, if you do like QED scattering, where some of the particles are magnetically charged, not only electrons, but also monopoles, non-invertible symmetries appear there. I actually gave a talk about this here last year. So there are many applications of these type of non-invertible symmetries, okay? So this is sort of motivation, a definition of what I mean by non-invertible symmetry, and a motivation as to why you should care, okay? Now, I do want to mention that this example that I gave you here, the IC model, this symmetry here, it's a little bit fake, okay? In the following sense. So if you take the IC model, which is the phi 4 to the theory, the phi 4 theory over there, and you gauge this symmetry here, if you compute so 1 with phi squared plus 5 to the 4, and you gauge the Z2 symmetry, this is identical to a free Majorana Fermi. Okay, this is the boson Fermi duality. Okay. And here we have this non-invertible symmetry, but after gauging, this becomes a regular Z2 symmetry, which is just the chiral symmetry. Okay. And in this theory, I told you that the sexting vanishes, but under duality, this is just this correlation function here. And this is clear that this is all under this symmetry. So in this frame here, the vanishing of this correlation function is natural. It's just a regular Z2 symmetry. And what I'm telling you is that in this frame, which is related by Z2 gauging, the same story applies to a non-invertible symmetry instead of a regular symmetry. So in this case, you don't need to know about this symmetry. If you knew about this theory here, you would also explain the vanishing of this selection rule. This selection rule here, it's kind of mysterious because it comes from something that doesn't have an inverse. But if you're okay with a Z2 gauging, you can go to another theory where here everything is a regular invertible symmetry. Okay, so that's why I say that it's fake. You don't need to care about this non-invertible symmetry. If you're familiar with this, you can forget about this. Okay, so this is called a non-intrinsic non-invertible. Which means invertible up to discrete gauging. Okay, so if you have some discrete gauging that you can do to your theory, that makes the non-invertible symmetry into a regular invertible symmetry, we call that a non-intrinsic non-invertible. And it's kind of non-intrinsic symmetries are a little bit boring because they will never teach you anything that a regular symmetry won't. Okay, if you understand regular symmetries and you understand gauging, then you also understand non-intrinsic non-invertible symmetry. Okay. So a very natural question that you could ask is, are there intrinsic non-invertible symmetries? Are there non-invertible symmetries that you could never understand by gauging and using regular symmetries? And the answer is yes. There are many non-invertible symmetries that are actually non-invertible in any dual description. Okay, so there are many examples in, for example, in two-dimensional CFTs. Many examples of intrinsically non-invertible. See, for example, minimal models have many of these symmetries, and people have used these non-invertible symmetries to explain some mysterious degeneracies that people had found in RG flows. For example, you have RG flows of minimal models. Sometimes you get degeneracies that do not make any sense until you realize that the degeneracies are reflecting one of these symmetries. Okay. Now, so far everything I told you was discrete, but let's move on to the continuous part of the talk, where things are going to become a little bit more interesting. Okay. So continuous symmetries, everyone here knows what a continuous invertible symmetry is. For example, if you go back to the scalar case before, so now you make this complex, then there's a continuous symmetry, which is the usual U1. Okay, this is a continuous symmetry because it depends on the parameter alpha that you can vary continuous. Okay, so this is a continuous invertible symmetry. But there are also non-invertible continuous symmetries. And you can do the same trick there of gauging. So for example, in this case, if you gauge the symmetry that takes phi dagger, if you gauge this, then U alpha becomes non-invertible. I actually didn't understand this thing very well until I read a paper of the year. So that was a very useful paper for me. I'm not going to mention references, but if you want to know more, please do let me know. So this is an example of a continuous non-invertible symmetry, but again, it's boring in the same sense as before. It's something that is non-invertible, but it comes from something that is invertible, and you're just making it non-invertible by some gauging here. Okay. So the question that we want to analyze here is the following. So question 1 is, are there intrinsically non-invertible PU symmetries? Is there some non-invertible symmetry that depends on continuous parameters, and that is always non-invertible regardless of any gauging? Okay, so this is one of the main questions that we want to ask, and it turns out to be very, very hard. But one thing that usually helps with continuous symmetries is Noether's theorem. So question 2 is that is there a version of Noether's in the non-invertible case? Okay, these are the 2 questions that we were trying to answer in the paper. Are the questions clear? Is there any question so far? Okay, so let me move on. Yeah, one thing that I have to say is that so far we only really have answers for 2-dimensional CFTs. But we believe we only have answers in this case for technical reasons. There's nothing fundamental. Nothing that I'm going to say really depends on the fact that here is 2-dimensional and conformal. We believe that there is some extension to any dimension and any theory, but we really needed some data that is only available for 2-dimensional CFTs, which is why I'm going to stick to this case. Okay. Okay, so let me begin with Noether's theorem. Okay. So the claim is that for every continuous symmetry, whether invertible or otherwise, invertible, or there is a current such that okay, so for every continuous symmetry there is a conserved current and vice versa. And the claim is that if the symmetry is invertible, then J nu is single valued. And if it's non-invertible, J nu has branch cuts. In other words, it's attached to a topological line, or in string theory language, it's a twist field. Okay. So this is the main claim, and before I try to give an argument as to why we believe this is the general statement, I think it's important to define a little bit better what we even mean by continuous symmetry. Okay, so first, what does it mean for a symmetry to be continuous? And the naive definition that something is continuous if it depends on a continuous parameter, that doesn't work, right? Because if I write, for example, U alpha to be 1 plus alpha C, where C is the Z2 from before, it depends on a continuous parameter, but you wouldn't call this a continuous symmetry because it depends on alpha sort of in a trivial way. So for us, a continuous symmetry is something that depends on a continuous parameter, but in a way that is not just a globe like a C number dependence. Okay.
That guy probably doesn't have defect states as well.
Yeah, no, I mean, well, yeah, he just said, yeah. Mm-hmm.
But if it did, you would be happy, right?
I wouldn't call it a continuous symmetry.
Just a continuous family of topological defects, why not?
If he has a defect Hilbert space, yeah, sure.
Okay.
I don't know if I would like to call it a continuous symmetry, it would be a symmetry, but I don't know. I mean, if the dependence on the parameter is like operator dependent, like these acting on different states give you different actions. This gives you the same action on every state. That's why I don't want to call it a continuous symmetry.
Why is that? It looks like it actually does act differently on different states. It just won't correspond to a line operator.
I mean, on every C even state, it acts as 2, and on every odd state, it acts as minus, as 0, right? So there is 2 sectors of the theory, and on every sector, this is a continuous, discrete thing. If you break the Hilbert space into even plus poly.
Alpha is the parameter, right? So the eigenvalues are 1 plus alpha, 1 minus alpha.
Yeah. So it's proportional to the in each sector, it's just the identity times C number.
That's true.
So that's I mean, it's fine. It's just a boring thing. I don't want to consider this type of thing a continuous symmetry. I want to be more restrictive in what I mean by continuous symmetry.
Mm-hmm.
Okay. So what is the proper definition of a continuous symmetry? I'm going to borrow a definition from the CFT literature, and I will define defect U alpha to be continuous if it has moduli, basically. It admits trivial, exactly marginal deformations. Okay. This is my definition of That's the definition I'm going to be using for what I mean by continuous symmetry. Okay.
So topological and
Yeah. Sorry. If it's topological, yeah. So it's topological. And it makes exactly marginal deformation. Okay. Oh, and by the way, this part of the discussion is almost verbatim from a paper of Ryan with Ivan Wang. Okay. So I'm gonna keep following. Okay, so let me begin by one direction in the theorem, which is if I have a defect that is continuous, this implies the existence of a conserved current. Okay. And so the fact that it's continuous means that it has an exactly marginal deformation. Okay. And so I take mu be by definition that marginal deformation. Okay, so if you have the defect like this, yeah, then there is some operator, J mu, that lives on the defect, which is exactly marginal. So delta is d minus 1. And if d is Lorentz invariant, this implies that the spin is 1. Okay. So for example, if I were to take, for example, d alpha to be e to the I alpha a mu, p mu, where these are the generators of translation, this would not hold because this is not Lorentz invariance. It depends on a vector here. But if you take something that does not depend on external vectors, something that is Lorentz invariant, then the current has to have spin 1.
Just to clarify, so that claim means that J mu is the deformation that is symmetry under U alpha. So what type of the claim is?
I don't think that it has to be necessarily, no.
What do you mean by then? Like, so yeah, I mean, you can have a exactly marginal deformation that breaks the symmetry that you are by generating from that.
So I'm defining a continuous defect as something that has an exactly marginal deformation, something that admits an exactly marginal deformation.
Like, what do you mean by a defect?
Basically, the deformation is whatever takes alpha to alpha plus delta alpha. So if it depends continuously on alpha, there has to be some operator that induces that transformation. If I want to shift alpha, I can shift alpha by inserting an operator on the defect. So
I see it.
that's the current J
That
is
is act on this problem. So
I'm shifted. See.
I don't quite know how you go from this to. I see. You're assuming that it's a local operator,
Yes, but it lives on the defect.
or it lives on the defect. Then you're seeing Lorentz invariance, makes it obvious that it's a vector.
I don't know how obvious it is, but yeah.
I guess that's what I was asking. Is this supposed to be a proof or a plausibility argument?
So if you take the definition, it means that there is some exactly marginal thing, and that implies this part here, right? I'm assuming that it has an exactly marginal thing. That's my definition of continuous. So that means that there is some local thing that lives on the defect, and it has that dimension.
1.
Well, this is the dimension, it's not the spin. The spin comes from the fact that it's Lorentz invariant. If it's not Lorentz invariant, the first part is still true. Well, no, it's not even true. Like it's gonna be, well, maybe it is true. I don't know. If it's not marginal, so probably, yeah. If the defect is not Lorentz invariant like this, then the thing that lives on the defect is the energy momentum tensor, right? Which has spin 2, not spin 1. So the spin could be anything. But if you impose that the thing is Lorentz invariant, then the spin has to be 1.
everything has to be topological, so you can also think about OP with the stress tensor. Probably get the spin out depending on what you do with the indices.
Right.
Why do you need the spin to be one?
I don't need it. I'm just claiming that if you impose that it's Lorentz invariant, it has to be spin 1. It comes from Lorentz invariance.
But in principle, spin 2 would also be.
Yes. But then the thing that you get from a spin 2 current is not a Lorentz invariant thing. For example, this thing is not Lorentz invariant.
It's hard to imagine how you would keep it topological though, while breaking Lorentz invariance in an interesting way.
Yeah, I agree. I don't know. But I mean, I
Like this is topological. I mean, space-time symmetries are still topological.
yeah, but it sort of stops there. I don't know.
Well, not necessarily, it might be higher.
But it's not generic, I would say. Yeah. So this is the argument for this part of Noether's theorem. If you have something that is topological and continuous, then there must exist some current that lives on the defect, and it has to be exactly marginal on spin 1. And you can in fact fold the defect around J. If you fold it, you end up with I don't know if I want to get into details here. Let me skip that for now. And let me do the opposite direction, which is given J mu, I can define a defect. Okay, so I'm going to assume some J that lives on some topological defect that I call B, such that delta is D minus 1 and spin is 1. Actually, I should have written could be plus minus 1 if you want to do 2 dimensions. Okay. The defect on where the current lives, it could be the trivial thing, and then in that case, J would be single value, or it could be a non-trivial topological defect, and then J would have a branch cut, which is basically P. And so what we need is some topological defect that makes J mu as an exactly marginal deformation. So how do we find a topological defect that has J as a marginal deformation? Well, B itself is such a defect. So I'm going to claim that B deformed by J mu is, okay. This is going to be the claim. And the way you do this is,
I thought B was an open thing that ends on J.
you can, I mean, you don't have to, it could be a closed thing. So if you have, so let me see, so into the, so I can draw something. If you have B with J that lives there, you can deform it into this, right? And then collapse it and you get this. So if you have something that lives on a defect, you can just pull it out and then contract everything. So if you have how to draw this in higher dimensions, you can do. And then collapse it and you get this. Sure. Okay. You can live on a defect, or I mean, if you have this, you have this, and if you have this, you can just bring it back to the defect and you have this, right? So these 2 point of views are the same. Kind of, I mean, it's a little bit subtle, but
Well, if I just give you L, I don't know if I can necessarily, maybe there are many P's, I don't know if I can.
yeah, nothing here is unique. There are many choices that you make everywhere in the construction, so you're not gonna get. I mean, I don't want to claim that the Noether's theorem is bijective. I don't think it is. But I think that's even true in the invertible case. Like if I give you a current, there is not a unique way to construct a defect that has that current, right? Like if you have U alpha and you have U alpha times C, where C is something discrete, these two have the same current. But when you exponentiate it, you're gonna get this one, not this one. So the construction for a given current, there's not a unique defect, right? So even in the invertible case, nothing is unique. You have choices that you make everywhere. Okay. So the way I'm going to define the defect is, again, borrowed from the CFT literature. It's called the binning field construction. So I'm going to define, let's say you have some correlation function and you want to insert this defect. This by definition is going to be the path integral. I'm going to insert the defect where the line lives. Then I'm going to do the action, the equal action, plus the integral of J. Let's say that you're inserting this on some contour gamma. So I insert the same contour and integrate there. Okay. So this is the definition of the topological defect here. So note that this is well defined because you're integrating J on B, right? You're putting J, the current and the baseline where the current lives, in the same position in space-time. Okay. It is topological and Lorentz invariant. So the fact that it's topological comes from the fact that delta is d minus 1. So that means that alpha basically is dimensional. It's an exactly marginal deformation. So this thing here doesn't depend on the shape of gamma. And you can also give a more traditional presentation, expanding the exponential in power series, and get it's just from 0 to infinity on alpha and where Qn, I'm gonna let me write the second one so that I can actually draw something. So here, this is the base. Here, putting one current. Here, I'm putting another current. And I'm doing this is gamma 1. This is gamma 2. This is gamma 1. Gamma 2. This thing here. Okay. This is Q2, but it's the same drawing for any number of currents. Okay. So this is a usual definition of another charge of another theorem, except that now you have a topological defect B, which is attached to the current. But if you were to remove B, this is the usual Noether's theorem. Okay. And you can prove that this is topological using the same argument in the Noether case. Okay, so you have to check that this commutes with the energy momentum tensor, and then the currents commute because they have dimension d minus 1, and B commutes because by definition it's topological, so everything here commutes with the energy momentum tensor. There are some details because you have to make sure that you know what to do when things come close to each other, so you have to be a little bit careful with ambiguities that appear, but it's doable. You need to do like a path order prescription, but that's sort of boring. It's in the paper if anyone is interested. Okay. So this completes the statement of Noether's theorem. If you have a defect that depends on a continuous parameter, then you have an exactly marginal current that lives on the defect, and vice versa. If you have an exactly marginal current that lives on some defect, then you can construct a continuum of defects using that current. Okay. Now I'm gonna include this specifically. Delta 1 is 1 is equivalent to h bar 1, 0 or 0, 1. Okay. So in 2 dimensions, the statement is that if you have some twist field of dimension 1, 0 or 0, 1, which I'm not going to repeat at the end on some topological line, then you have a continuum of defects and vice versa. Okay. And so this is the answer to the question of whether there is a Noether's theorem for non-invertible symmetries. Now let me go back to the other question, which was, are there examples of this type of thing, but where the symmetry is intrinsically non-invertible? Okay. Go back to question 1, which is intrinsic. The answer is that V is non-intrinsic. If and only if there exists some gauging that makes J log of single value. In other words, if there is some gauging that makes B transparent, then the effect becomes invertible. In other words, it's not intrinsic.
So the same as saying that B is a condensation defect. Maybe not quite.
No, I want to say that it's truly transparent, but
Oh, but I mean, if B is a condensation defect, then can you make it? You can always make it transparent.
okay. I'm not sure if that's true, but you might be right. Yes. I'm not entirely sure. Okay, a good point.
I mean, it's not more like what can gauge real.
Well, you can call it. I want to know if there is some algebra object that when I condense it, B disappears. You can call that gauging B. Yes. I want to know if B can be gauged away. Yeah.
Feels more restrictive than just having a condensation defect, or different because you want to condense that line that the twist field ends on, or that the twist field is the end of everywhere.
Right.
Not just being able to do it on a surface. So
Yeah, I guess I was asking if B is a condensation defect, then is this always possible, and vice versa. If it's always possible, can you always write B's? But I think one direction might be true, but the other seems fine.
Okay, so this was all very abstract. Let me give you a few concrete examples so that things make more sense. And again, all of the examples that we have are in 2 dimensions because we really don't know the spectrum of defect operators in theories that are not 2-dimensional CFTs. So I don't know any example of something with these things except in 2-dimensional CFTs. If anyone has an example of something like that in high dimension, please do let me know.
But it can't, sorry. What defect would you want them to end on? Like a line or codimensional one?
It doesn't matter because once you have something, you can start following it, and then it also gives you. In 2 dimensions, it's super easy because they only have line. You have nothing else. In high dimensions, we don't really have a super sharp statement. Once you have something that lives on this, let's say, whatever, you can collapse one of the dimensions and it becomes plane. So if it lives on a volume, it also lives on a plane. Usually, doesn't have to because when you collapse something, you might get the 0 operator. So there are some subtleties.
Using lines are, especially in 4 dimensions, hard to come by. Very non-generic.
Yeah.
You want, if it's sufficient on the surface or something.
I would say it's sufficient on the surface, yeah.
I was gonna say, like, can you just, as I think we thought about in our old paper too, like that you just gauge a charge conjugation symmetry and then it projects out the current as a local operator.
Sure, yeah.
You get a family of these like basically like these cosine guys, right?
The more interesting question is whether there is something that does not come from gauging. That's
Okay, so you're asking specifically about specifically about the intrinsic ones.
yeah. Mhm.
And so if you get gauge charge conjugation, you get a Z2 or something. Stuff a lot.
Yeah.
But like at least in 4 dimensions, those are pretty non-generic, and it typically comes from just such an operation.
Yeah, somehow we thought in the past that they all came from gauging, but I don't know. I just tried very hard.
Yeah, exactly. They would, no, I think that bias is probably still, because we don't know any examples where they don't come from gauging.
In 2 dimensions, we do have examples, but well, it's not clear if you do, but yeah, let me.
Right, so you're gonna show us that.
So the simplest example of a 2-dimensional CFT are the minimal models, right? And you can ask the question: is there some twist field with h bar 1,0? And the answer is no. So there are no continuous symmetries in minimal models, which you might have expected that because minimal models are extremely rigid, so you don't usually expect any continuous structures in minimal models. So this example doesn't have any continuous symmetries, neither invertible nor non-invertible. The next simplest example are the C+1 models, and here you do have yes to 1,0 twist things. And so if you run the construction that I told you there with these twist fields, you reproduce all the continuous symmetries that were known in the literature, the cosine type symmetry that Ryan and Theo know about. So these, so the list of all 1,0 twist gives you the list of all known continuous symmetries. And we claim that the list stops there because for any continuous symmetry you will have a twist field. So you take all the twist fields that satisfy the condition that has 1,0, and that gives you the full list of non-invertible symmetries. But these are all non-intrinsic.
Right. Do these things in general lead to, so if you have a standard current, then you can, in principle, attempt to construct a marginal operator, not just on the line, but also at the bottom.
Well, it's
That also
not
true
necessarily exactly
It may
marginal.
not be, but yeah.
We don't think it is true in the non-invertible
It's
case.
not true.
In some special cases, yes, especially the non-intrinsic ones. The non-intrinsic ones are so boring because they are invertible in some dual frames. So those, it might be the case, but in the generic case, we don't think because, for example, most of these 1,0 currents, they don't even satisfy the current option. The OD is not closed. So it's a very non-constrained option.
The C+1 guys are cool though. Like if you're on the orbital branch, even though it doesn't have any like ordinary continuous symmetries, you have these non-local currents. You can construct a stress tensor from that, like the sugar aura. You can also have
The
like
margin operator.
yeah, you can get the marginal operator. You get this like twisted Katsumudi algebras that Hotep talked about.
The E8 points don't have any continuous symmetry. Or do they?
I think they do.
Yeah,
They do?
so do yes.
What?
I have to double check, but I think they do. I'm not very sure.
I
mean-
the isolated.
Yeah, I'm not sure.
So the ones in the C+1 moduli space, those isolated points would have. But I guess it's true that they can't have marginal operators.
They're isolated. They're not.
They're isolated.
Yeah, but they have
They have
equals one.
continuous.
They do.
Yeah, because they're gauging. You can get them from gauging with the SU2 point.
Yes.
So you just gauge the currents as well. They just sit on like non-invertible lines. That's probably why you can't make marginal operators out of them.
So it's SU2 connected to a non-invertible line.
Exactly. Yeah. Very cursed curve. With like some two-dimensional curve. Like custom. 3D
Okay, so here you have two examples, one that doesn't have anything at all, one that does have these things, but they are non-intrinsic, so they're a little bit boring. And let me move on to the third simplest CFT, which are WZW. And here we do believe that we have some that are intrinsic, although it's very, very hard to prove. Okay, so here we have many infinite families. Of GA models that have 1,0 cards. We have many, many examples where you have non-invertible continuous symmetries. Now the question is whether they're intrinsic or not. This is very, very hard. So in order to prove that something is non-intrinsic, you have to find some gauging that makes it invertible. But in order to prove that something is intrinsic, you have to prove that no gauging makes it invertible. And that's super hard because you would need at the very least to classify all gaugings. And in general, we have no theory where all the gaugings have been classified, except for the minimal models. The minimal models is the only theory where all the possible discrete symmetries are known. In the WCW models, we don't know the full list of symmetries, of discrete symmetries. So we don't know if there is some obscure unknown discrete symmetry that when you gauge it, you make these currents local.
Okay, gauging means gauging a standard 0-form symmetry, or do you mean some kind of?
Anything. Yeah, could be.
Well, that's pretty open.
So that's proving that something is intrinsic is not really doable. You can prove that it's non-intrinsic by finding the right gauging, but proving that something is intrinsic, it's extremely hard. Okay. So there is a more reasonable task, which is we do know the full list of gaugings that commute with the chiral algebra. So these are the modular invariants of the theory. Okay. And so you can ask, is there some gauging that commutes with the chiral algebra and that makes the current free? So this is a more restricted question, and for this one, we do have an answer. Okay. So this doesn't prove that there is no gauging, it just proves that there is no gauging that is symmetric, that respects the symmetry of the theory. Okay. So for example, in the SU2 case, all the gaugings, all SU2 invariant gaugings are given by the AD classification. And you can check one by one if any of these makes the current single valued or not. And the answer is that for K equals 4, 10, and 28, it's non-intrinsic. Meaning that there is some gauging that makes the current single valued, but for the rest, okay, it's SU2 conditional intrinsic. If you impose that you're only going to allow gaugings that commute with the SU2 symmetry, then there is no gauging that makes this thing a local thing. Okay. So this means that these non-invertible symmetries in the SU2 case, they give you selection rules that maybe follow from some invertible symmetry in some dual description, but in that dual description, you will not have the SU2 symmetry. So if you want to put as many constraints as possible in your theory using the SU2 symmetry and the non-invertible symmetry that I'm telling you about, then the symmetry has to remain non-invertible. This symmetry, you can never make it invertible if you also want to have the SU2 symmetry at the same time. So this is almost as good as being intrinsic, right? Because who cares if there is some gauging that makes it invertible? I'm telling you, if you want to have the SU2 symmetry, that does not exist, okay? In these cases, it's actually interesting if you look at this. In these cases, there is some gauging that makes it invertible. And if you actually perform that gauging, the theory becomes SU3 level 1 in the case of K plus 4, SO5 level 1, and G2 level 1. And the currents there become the currents of these symmetries here. So for these cases, that becomes a local current, and it's a current that we already knew was there to begin. But for the rest of values of K, there is no such gauging.
Let the sequence continue.
Huh?
It's the beginning of some.
No, it's I mean, yes, there are. So the AP classification is infinitely long. So there are many gauges. My claim is that these are the only gauges that make that thing local. The rest of gauges do not make it local. So yeah, the sequence continues, but the gauging will not. The symmetry will remain non-invertible if you perform those gauging.
This is for one instead can be with SU2.
Yeah.
Yes. What makes this complete classification for W models hard for all the agents? It's just because there's an external.
No, I mean, if I give you just the simplest theory, like take a free boson in whatever dimension, like 4 dimensions, and I tell me all the symmetries of the theory. We don't know. I mean, we know many symmetries, but we can never prove that you're done, right? Like if I give you the symmetries of this, how do you prove that nothing else is there? There's always the possibility that there's some symmetry that you are missing. So we don't know the list of all symmetries in any theory except the minimal models. The minimal models are the only theory where we have a full list of symmetries. For any other theory, I mean, the standard model we know that there is like U1 bearing. Is there anything else? We don't think there are more symmetries in the standard model, but how do you prove that you're done, right? There's always the possibility of some very non-trivial duality that gives you some. We don't expect that to be true, but proving that it's not true, right, it's very hard.
But in this restrictive setting,
Mhm.
someone was able to prove that you are done after the AD classification.
Yes. Well, we took the AD classification and proved that using the classification, these are the only cases where it's doable.
Right, but you were also saying before, right, that these are the only discrete symmetries that lead tensor to invariant,
Yes.
and there's nothing.
Yeah. So this is, we believe, the first example of a continuous symmetry that is intrinsic. We don't know if it actually is, but we really suspect that it is intrinsic. And we don't know any other examples in the literature of a continuous non-invertible symmetry that is intrinsically non-invertible. Okay. So I'm almost out of time. Let me tell you a few loose ends that we didn't that I didn't have time to tell you about in detail, or some things that we would like to do in the future, but we haven't done it so far.
Sorry, with this new understanding, can you now make some? Did you make some non-trivial predictions of like selection rules for correlation?
That's one of the loose ends. Yeah. Thanks. I'm gonna tell you. So the first thing that you would like to do is what are the word identities of the defect that I just told you exist. There's gonna be some constraints on the correlation functions, and in principle that's the prediction. I'm gonna tell you that there is some combination of correlation function that has to vanish. The problem is that in order to do this, we need to know how D acts on local things, right? And we don't know how our defect acts on local operator. So we don't know what the constraints are. We believe that we know that there has to be some constraint on the correlation function of the theory. We don't know what the formula for that constraint is. Okay. So what we did is we figure out the infinitesimal. So if you write the alpha as 1 plus Q1 plus 1 half of Q2, so alpha squared. We know how Q1 acts on the local operator. We don't know the full action. So we know the infinitesimal action. So in the invertible case, you know that Q on phi, this is like alpha phi, right? This is the infinitesimal action of a U1 symmetry and a local field. We know the version of this in the non-invertible case. This is the infinitesimal action. The finite action is like phi goes to E alpha phi. This we don't know. This we don't know. Okay. The action of Q1 on a field, it's a complicated thing that you have to sum over some lines that appear in the product of the baseline that I did here with some F symbol coefficient with some like the structural constants of the algebra, etc. So it's a very complicated formula that depends on lots of data that we don't usually know very well, like the F symbols, we only know them in some special cases. So even at the infinitesimal level, it's a very complicated action, but it's a non-trivial action. So this is like the first step to finding the action on local operators. And once you know the action, you will know the word item. So to answer your question, we don't know what the constraints are. We know that some constraint exists. It's a non-trivial constraint because this action is a non-trivial action, but we have no idea what it looks like in detail. More applications, there are applications that go beyond selection rules. So once you have a continuous symmetry, you'll have selection rules, but there are other constraints that you get from symmetries that are not just selection rules. There is a nice example that I'm not going to describe in a lot of detail, but there was a recent paper by Antinucci and collaborators where they argue that if you have a continuous symmetry on a product theory, CFT, not CFT bar, this implies defect conformal net. In one of the, so if you take the square of a theory, you find a continuous symmetry, then in the individual theory, you have a conformal manifold of interfaces, which is something that you don't usually find without symmetries. And so, for example, using this, we show that minimum models, for example, minimum have sometimes for some special minimum models defect conformal manifolds. So even though minimum models do not have any continuous symmetries, they do have continuous interfaces, which is something that we did not expect at first because minimum models are so rigid, we didn't expect any continuous structure. It turns out that they do have something continuous there. So this is one example of an application of a continuous symmetry. Other open questions are, I would like to flesh out all the details in the high dimensional case. There are some subtleties that we don't understand very well. So everything I said here, we are convinced in the two-dimensional case. Some of the things that I said in the high dimensional case, we are not entirely sure. I also would like to know what the precise statement in the non-conformal case is, because the way I phrase it requires conformal language. I need to know the scaling dimension. We don't know what the correct statement is in the case of non-conformal theories. I would like to understand that better. I would also like to understand better the case of almost continuous symmetry. So for example, in 4D, there is the AVJ symmetry, where the alpha is only defined for rational alpha. So it's not continuous, but it's like it's almost continuous, like a dance on the real line. So we don't really know what the statement in this case is. We don't know if the construction that we did here, there is some generalization that also includes this type of thing or not. That's an open question. Another open question is,
do we mean continuous by flat gauging? I don't know. Well, flat gauging is not quite the same as discrete. Well,
that part of the, yeah, we don't know what we. The problem is that there is some construction of this thing that looks very similar to the things that here. The current for this is 5. That's F. What should I do? This is conserved, but it's not gauge invariant.
Sure.
So it sort of lives on some, like, there might be some defect that you can attach to the current to make it gauge invariant, similar to an electron kit, not gauge invariant, but if you attach a Wilson line, you make it gauge invariant. There might be some thing that you can attach to this thing to make it gauge invariant. And so in that sense, it sort of looks like the same story. There is some conserved current that lives on some defect, but we haven't been able to really flesh out the details. The case of the question of flat gauging, that's also not understood to us basically at all, is to me. More open questions. There's in the last year or two, there were lots of papers on quantum groups in the CFT literature by Gabay and collaborators, and many of the formulas look very similar to ours. So we would like to understand if there is some connection there. Another open question is, what is the precise mathematical formulation of these things? What is the right category for continuous symmetries? We have no idea. More open questions, what happens in holography? In holography, we know that continuous symmetries are dual to gauge fields, so we don't know if these continuous symmetries, these continuous non-invertible symmetries are dual to anything. We don't know. In quantum gravity, we say that all symmetries are broken, so these things should also be broken in the bulk. We don't know if there are some interesting physics in the bulk from these type of symmetries. Another very important question is what happens to anomalies of continuous symmetries. In the invertible case, we know that anomalies can be diagnosed, for example, by taking OPE of currents. Here we also have a current, so we can study the OPE of these things and see if there is some notion of non-invertible anomaly. But it's a very tricky thing because these things do not even satisfy a closed algebra. So we don't know if there is a meaningful notion of anomaly in the non-invertible case, or maybe there is, but it cannot be detected by taking OPE of currents, etc. I have only began scratching the surface of these things here. We think there are a million interesting questions that one could ask about these things here. Thank you very much. More questions?
I mean, I think a basic feature of this intrinsic current, like non-zero current, is they cannot live on the boundary of the invertible symmetry, because otherwise the spin would immediately imply that the symmetry can gauge.
Yes, yeah, correct, yes. So if the thing here is anomaly free, then you can always gauge it, yes. So the interesting case is when this thing has an anomaly. Yeah.
It basically must be non-invertible.
It must.
Otherwise, the spin selection rule.
I think I agree. Yes, I think there might be some weird non-perturbative anomaly that doesn't just come from the spin. Maybe I'm not sure.
For Z, it's definitely true.
Yes, but I don't know if in more generally. Maybe you're right. Maybe in the invertible case, just the spin is enough. Yeah. Mm-hmm.
Are you able to say anything about like the global like what's the space of alpha?
No.
Or like what information you would need to in order to answer? Okay.
I mean, at the very least, you would like to know the fusion rules of this thing, right? Like in the invertible case, by fusing things, you at least get some information. We don't even know the fusion rules of these things. Yeah, we have no idea. We don't have anything.
It's also not obvious whether D alpha has a good dependent space.
Well, in the definition that I gave you in terms of a path integral sort of tells you that there is a Diffie-Hillbert space because I'm doing some exactly marginal deformation on a topological line that has a Diffie-Hillbert space. So I have a Diffie-Hillbert space for this thing, and I'm just doing an exactly marginal deformation of that Hilbert space. So you do have a Hilbert space for any alpha. So yeah, the path integral formulation sort of tells you that you do have a Diffie-Hillbert space.
I add to your list of open problems.
Sure, please.
One question I always thought was kind of interesting with these things is whether you could have a theory which has ordinary continuous symmetry in the UV and then something funny happens to it, and then in the IR it becomes the current kind of becomes emergently gauged. Tried to do this in all kinds of lattice models, but couldn't figure out it's possible whether this could give you some.
I would expect the opposite, right? Like you begin with something non-invertible and becomes invertible in the IR because everything that was making it non-invertible is sort of massive and goes away. But the opposite, it seems hard to imagine.
Even that would be interesting, though.
Yeah.
I don't know.
It seems more doable, I would say.
Yeah, it's definitely a symmetry transmutation, but between like invertible and non-invertible things.
I'm thinking if there is some easy way of constructing like some example of that. No, but yeah, it's definitely interesting.
There's something like so boring. Start with something that has a Z2 line attached, and then you Higgs the Z2 and it becomes local. But
yeah.
That's an example of the second kind of want the opposite.
Yeah, I guess that's a good example too. So Yeah, I want the opposite. I think the opposite would be cool because like,
Well, my first reaction is that the opposite is not possible, so I
Uh-huh.
have to elaborate.
that'd also be interesting.
I mean, if you start with it's very naively, right? If you started the UV, the
Yeah.
local operators,
Uh-huh.
what are you imagining happening?
Well, I mean, you can definitely have this thing where charges like become sort of emergently gauged, that like that there really are local operators that create this particle, but those are extremely heavy, and the ones that remain light are the ones that are attached to like lines which become Wilson lines.
Something
I can
that
tell
could
you
only
that.
happen on the lattice, I would say, no?
Yeah, it's easy to engineer on the lattice.
In the continuum, it seems like sort of.
I think we can engineer in the
No,
continuum too.
you know,
I mean, if you have a line at some scale, you're gonna have it, you might go away in the IR, but it will never go away in the UV, I would say.
well, as long as you're willing to start with something local that's heavy that then decays into many things that are fractionalized, is that enough?
That's sort of what has to happen.
No, but that's easy to engineer, because you can take QCD in the range where it's, let's say, infrared free and start with a barrier. It will fractionate into fractional quark, charged quarks.
Mhm.
Is that what you have in mind, or something even more dramatic?
Well, I would have to think about it. Maybe we should chalk off line. I just wanted to add it to the list.
Any other questions for Diego? Yeah, looks like we got